My name is Matt Westervelt, and I'm the owner of Metrix CreateSpace, a hackerspace in Seattle, Washington. Back in November of 2011, Peter Zatko from DARPA came by to tell the Seattle hacker and maker community about their new research funding program called Cyber Fast Track, or DARPA PA 1152. It seemed like an interesting idea, but as a new business, and a relatively new business concept, we didn't believe we had time to come up with a project or have the resources to put something out. Fast forward to 2013, and the landscape here has changed. We've got better capabilities, more staff, and a community of great people to pull from. We decided to see if we had what it took to get the interest of the people that brought us the internet. On April 1st, the last day of the program announcement, we submitted a proposal which we believe could be of interest to both DARPA and the ad hoc cyber research community. Hackers. An open, unobtrusive electronics platform for use in textile applications. Something that we believed we could design, prototype, and build completely in-house. We wanted to be able to build it with as few outside dependencies as possible. We would release our results into the public domain so others could build on our work. We saw the opportunity as a unique chance for the government to invest in our community, help out the shop, and put something interesting into the world. We also knew it was a long shot. Luckily, DARPA dismissed the funny timing of our submission. They saw something in it that they liked, and they approved our summer-long project. In the first quarter of the year, we had started the process of getting the LPKF ProtoLaser S as an in-house tool. We knew that this was going to change the way that we as a community looked at electronics and rapid prototyping. And we knew that for this project, it was going to be an essential part of getting what we had imagined in our heads into the real world. What the ProtoLaser enables us to do is to create advanced circuit boards in-house using a completely dry process. Much like a 3D printer or a laser cutter, we knew that having this process be publicly accessible was going to change everything. What we hadn't really realized at that point was just how flexible the laser could be. Our project, at its simplest, is a microcontroller project. We'd make some boards, we'd sew them into clothing, and we could see if we could get jackets and pants to talk together seamlessly. The details, they get hairy pretty fast. To do something that we were truly proud of, we knew we were going to need to do some real research, learn about some materials, invent some new processes, and take on a lot more than we'd outlined. Microcontrollers, electronics, textiles, they're all pretty well known at this point. Putting code on computers, making circuits, sewing fabrics, these are all common tasks at a place like Metrix. What we saw in this was a research opportunity beyond just cool clothing. It was studying the state of power storage and delivery that exist out there today and seeing if we could get our fingers into the state of the art. We used the internet, thanks again DARPA, and we found papers and articles and videos about graphene, a molecule-thick plane of carbon molecules that have amazing electrical powers. We learned that supercapacitors can be built using lasers. And although research exists, there are very few actual applications in the world today. We figured that we could take that state of the art and we could push it just a little bit further. We decided to see if we could pull off a textile-ready electronic that receives its power wirelessly and stores it within the laminated substrate in a graphene supercapacitor. Here are the results of our work.
Ideally, these devices will be unobtrusive and easy to use. To facilitate this, charging the devices must be done without requiring a change in behavior from the user. This can be accomplished by integrating the charging device with a person's hamper, clothes hangers, or dresser drawer. When the clothing is placed in these locations during the course of normal use, wireless power transfer methods can be used to charge a small supercapacitor on the device. We decided to transfer power wirelessly using inductive coupling. A prototype power transmission system has been designed and tested as a proof of concept. We constructed a large primary coil to transmit power, and smaller secondary coils to receive the power. The power transmitter uses a Class E amplifier to drive the large coil. Currently, we use a DC power supply and a function generator to drive the amplifier. The function generator gates a MOSFET at the transmission frequency. The MOSFET is in parallel with an inductor-capacitor combination, and a high amplitude is induced across the coil. Here, we have a test coil for the wearable device. It's a 2-layer inductor, and we form an LC tank with a matching capacitor. The coil and capacitor resonate at the same frequency as the transmit coil. To demonstrate this setup, we wirelessly power an LED in series with the capacitor and inductor. We're able to transmit a usable amount of power a distance of about 5 centimeters. The orientation of the secondary is important in determining the amount of power received. The secondary coil can also be integrated into this wearable device. We can then use a full wave rectifier, these diodes, to generate a DC voltage from the received sinusoidal waveform. This DC voltage could be used to charge a graphene supercapacitor that will be integrated with the board. This prototype shows the viability of wirelessly powering these devices. It's capable of providing enough power to trickle charge a supercapacitor. Future versions of the power transmitter could use miniaturized drive circuitry and a frequency tuned for peak power transmission. If used in a hamper or drawer, the drive coils can be enlarged to increase usable range. With 3 coils on different sides of a hamper, omnidirectional power charging is possible.
We have been working non-stop to get all of the elements of our project design goals into a physical model. To maintain a small footprint, we switched from a single-sided to a double-sided inductor. Integrating the capacitor into the device has doubled the time to manufacture. And in order to get as much prototyping as we could in the time we had available to us, we made scaled-down versions of the capacitor, so we could have enough time to run them through the laminator and continue on with other aspects of the project. We got surprising results with not only structural integrity, but capacitance as well after they came out of the press. Graphene is a time-consuming material to work with. To process a capacitor with a laser, we must first make a graphene film. This is done by applying small amounts of the aqueous graphene oxide solution to a substrate and letting the water evaporate. Once an adequate amount is dried to the material, we can then proceed to structure the capacitor. Once structured, we then apply an electrolyte solution of PVA and phosphoric acid. This must then be cured. Once cured, we can run the pressing operation. After 5 revisions and countless spur-of-the-moment changes, I'm confident to say that we have a viable, reproducible platform that can be implemented in not only cross-garment communication, but many other real-world applications as well.